Alright, what's going on everybody? In this video we're going to discuss binary search trees. But first we'll need to know what a binary tree is. A binary tree is a tree where each node has no more than 2 children. That's why it's binary. In this example, node 1 has 2 children, 2 and 3, and each of these children have their own children. They have no more than 2 children. Nodes 4 and 5 are the children of 2, and nodes 6 and 7 are the children of 3. In this similar example, this would also be a binary tree. Node 3 only has 1 child, node 6. But with a binary tree, no node has more than 2 children. Since node 3 has 1 child, that's fine. But if node 3 had 3 children, well, that would no longer be a binary tree. Now, what makes a binary search tree different from a binary tree is that the values are arranged in a certain order. Here's the order. The root node should be greater than the left child, but less than the right child. 4 is greater than 2, and 4 is less than 6. That's the pattern that this data structure is built around. If we take a look at some of the subtrees, let's say this one, 2 is greater than 1, but less than 3. And in this subtree, 6 is greater than 5, but less than 7. If done correctly, starting at the root node, the leftmost child should be the least value, and again, starting from the root node, the rightmost child should be the greatest value. The reason that these nodes are arranged this way is for quick lookup. Let's say we're looking for 5. What we'll do is compare 5 to the root node. If 5 is equal to the root node, well then we found our answer. If 5 is greater than our root node, we will move down to the right branch and do the same thing again. Is 5 equal to 6? No, it's not. However, it's less than 6, so we know to go down this branch. The runtime complexity to find a value within a binary search tree is big O of log n in its best case. So let's code a binary search tree now. Okay, let's begin. Let's create a node class, file, new class. I will name this node, and finish. Nodes will have some data, maybe an integer this time, int data, and the node class should contain at most 2 nodes. Node left for the left child, and node right for the right child. If a node is a leaf node, well then these will be null, but we would still like to allocate space to hold children. And within the constructor, we will pass in some data, int data, and assign it. This dot data equals data. Now let's create a binary search tree class. File, new, class, binary search tree. And within our main class, let's instantiate a binary search tree object. Binary search tree, I'll name this tree, equals new binary search tree. And within the binary search tree class, each binary search tree should have a root node. Node root. Here are some methods. We'll need an insert method to insert nodes. Public void insert. And there is a parameter of a node. Node node. Now let's create a second method. This next method will be a helper method of the insert method. So the insert method is going to call its helper method. And this will be private. The return type is node. Insert helper. We need a root node. Node root. And a node. Node node. In order for our program to compile, we do need to return something, so just as a placeholder, I'm going to return null. Okay, for the next method, we need a display method. Public void display. And a helper method. Private void display helper. And this has one parameter, a root node. Node root. Next method is a search method. Public boolean, we're returning a boolean, search, and the parameter is int data. And we will need a helper method. Private boolean search helper. There are 2 parameters, node root and int data. Again, we do need to return something. I'm going to return false just as a placeholder. Okay, next method is a remove method. Public void remove, and the parameter is int data, and we'll need a helper method. The return type is node remove helper. The two parameters are node root and int data. We do have to return something, so as a placeholder, I'm going to return null. Our remove helper method is also going to rely on two separate methods, one to find a successor and another to find a predecessor. This is in case we're deleting nodes, we have to shift nodes around. So this will be private int successor, and we will pass in node root. And we need to return something. Let's return 0 as a placeholder. And let's copy this, paste it, and this will be method predecessor. And that will be it. So let's close these for now and begin with the insert method. So with the insert method, we will assign our root node equal to insert helper method, pass in our root node, and node. So the reason that we're using helper methods is that we'll be using recursion. So it's a lot easier to use recursion if you have a helper method. Within the insert helper method, let's declare int data equals our node's data. Node is the node that we're passing in to insert. So let's check to see if our root node is assigned or not. So if our root is equal to null, then we should probably assign this node to the root node because, well, this is the first node. Root equals node. Return root. If root is not null, we have to compare the data to see if it's less than our root or greater than our root. Else if our data is less than the data of the root node, then we are going to assign this node as the left child of our root node. Our root's left child, root.left, equals, and we will use recursion, insert helper method. Pass in our root's left node and our node. The root node is going to change with recursion. At first, it's going to be the root node of the entire tree. After recursion, we're examining the root node of a subtree. So if we're passing in the left child of the original root node, well then that left child is now the root node of a subtree that we're currently working with. So else if the data is less than the current root node, we go left. If it's greater than the root node, then we will go right. Else root.right, that's the right child, equals insert helper method, pass in root.right and our node. And it's the same process all over again. And at the end, we will return the current root node. Okay, that is it for the insert method and the insert helper method. So let's insert a few nodes, although we can't yet display them. Let's insert some anonymous nodes. Tree.insert, and we can pass in a node, either a node name or an anonymous node. So let's pass in some anonymous nodes. Let's pass in the number 5, or some other number of your choosing. And let's pass in a bunch of numbers. How about 1 and 9? Make sure these are not in order. 7 and 3, 6, 4, and maybe one more. 8. If you run and compile this, there is nothing obvious that really happens. So let's work on a display method next. So with the display method, we will invoke our helper method. Display helper, pass in the root node. Within the display helper method, we're going to check to see if the root node of our subtree does not equal null. So if root does not equal null. If you would like to display these in order, we can use in order traversal, and that uses recursion. So invoke the display helper method, pass in the root child's left node, root.left. If we're using recursion, the first piece of data that's displayed is the least value, and these values will be displayed in increasing order. Technically, the term is non-decreasing, but think of it as ascending order. So the very first value is going to be the least one, followed by the root node of this subtree. System.out.println root.data. In our first subtree, the data all the way to the left is 1, and the root node of that subtree is 2. Then we need the right child, which should theoretically be 3. So again, we'll invoke the display helper method and pass in the right child. So this is in order traversal. All of the nodes will be displayed in non-decreasing order. So let's try this. At the end of our main class, let's invoke tree.display and see what happens. Yeah, there we go. All of the nodes within our binary search tree are now in order. If you would like this in reverse order, you can just change these methods around. Replace left with right and right with left. And these are now in decreasing order. But let's change that back. Okay, up next we have the search methods. Okay, search will return, then invoke the search helper method. Pass in our root node, as well as some data. Within the search helper class, we'll check to see if root is equal to null. That means our tree is empty, so of course we can't search for anything. Return false. Then add else if our root.data is equal to data. That means we found the data that we're looking for. There's a match. Then we're going to return true. We found what we're looking for. Else if our root's data is greater than our current data that we're looking for. That means we need to go left. So return, then invoke the search helper method, pass in the left child, root.left. And the left child is now the root node of this subtree. And then you need to pass in data as well. Else, we go right. So copy this, paste it. Return search helper root.right and data. And we can get rid of this return statement at the bottom. Okay, let's try this. So at the end of my main class, let's use a print line statement, and I will type tree.search, and let's search for 0. None of my nodes have 0 as a piece of data, so this should return false. Let's search for 1 now. That returns true. There's a 1 within one of my nodes. What about 9? That is also true. And let's try 10. And that is false. Okay, so those are the search methods. And lastly, we have the remove methods, as well as successor and predecessor. Now these methods are going to be a little bit tough, but I'll try my best to explain it. So within an if statement, let's check to see if this data even exists first. So let's invoke the search method and pass in our data. So this returns a Boolean, true or false. If we do find the data that we're looking for, then let's invoke the remove helper method. Pass in our root node as well as our data. Then within an else statement, and this part's optional, let's let the user know that we can't find that data. Data plus could not be found. So just to test things real quick, I'm going to remove some data that doesn't exist. Tree.remove 0. 0 could not be found. Now let's move on to the remove helper method. The first thing that we'll do is check to see if our root node is equal to null. If our root node is equal to null, then let's return the root node. Then within an else if statement, let's check to see if the data that we're trying to remove is less than the data of our root node. If it is, we need to go left down the binary tree. Root.left equals, then invoke the remove helper method. Pass in the left child of the root node, root.left, as well as our data. So we're going to go as far left as we can. Then add an else if statement. Else if data is greater than the data of the root node, then we will go right. So let's copy this, paste it. Root.right equals remove helper, pass in root.right, as well as our data. then add an else statement. If we reach the else statement, that means that we have found our node, and I'll just add a note to explain that. If the node we're trying to remove has children, that kind of complicates things, then we have to shift the nodes around. But first, let's check to see if it's a leaf node, then that's really easy. Within an if statement, we will check to see if the left child is equal to null, and the right child is also equal to null. That means that the node that we're trying to remove is a leaf node, and that's really simple. We don't need to shift any nodes around. We can just set this current root node equal to null. However, if the node we're attempting to delete has a right child, we'll have to shift those nodes around and find a successor. Else if root.right does not equal null, that means there's a right child, and we need to find a successor to replace this node. So we will assign root.data is equal to the successor method, which will find a successor for us, and pass in the current root node. Then take root.right equals and invoke the remove helper method, pass in the right child, root.right, as well as root.data. So when we delete a node, that will create a gap. And if there's a child, well, we don't want that child to be lost. We don't want that child to become an orphan. So we will link a child to that spot where we deleted a node. Now, if there's a left child, we have a slightly similar procedure. So we can use an else statement. Take root.data and invoke the predecessor method. Take this line of code, paste it, root.left equals remove helper method, pass in the left child of the root node. This else statement will find a predecessor to replace this node. And at the end, we will return root. So we can close out of these two methods, and we can open up the successor and predecessor methods. What we're doing with the successor method is that we're attempting to find the least value below the right child of this root node. We will assign the current root node equal to root.right. Then within a while loop, we will take root.left and check to see if it is not equal to null. While this condition is true, take root, set this equal to root.left, and at the end, return root.data. So what's happening here within the remove helper method, if the node we're trying to delete has a right child, we need to find a successor to fill in that gap. And that successor should have the least value. So we will go right and look as far left as we can, because values on the left are less than the root. Numbers on the right are greater than our root. After going right, we will go as far left as we can to get the lowest value, then return it. So that's what we're doing when we're assigning a successor to fill in that gap when we delete a node that has children. And then the predecessor method is going to be very similar. We will find the greatest value below the left child of this root node. So we can copy all of this, paste it. This time we will go left, then go as far right as we can go. I do apologize, this is a lot to take in. Recursion can be very confusing. But yeah, that's everything. Let's attempt to remove a node. So before we display our tree, let's take tree.remove, then pass in the data of a node you would like to remove. Let's remove 1. And here are the remaining nodes. We have 2 through 9 all in order. Let's remove 5. Okay, 1, 2, 3, 4, 6, 7, 8, 9. Let's remove 9. 9 is no longer there. And let's remove a node that is not within here, like 0. 0 cannot be found. Alright then everybody, that is a binary search tree. Just so you're aware, the order in which you insert nodes into a binary search tree does matter if it's unbalanced. Technically, my tree follows all the rules, however, it's fairly lopsided. There is a way to balance binary trees, but that's a topic for AVL trees. That's why the runtime complexity has a best case scenario of big O of log n, but a worst case scenario of big O of n, depending on how balanced it is. But basically, a binary search tree is a tree data structure where each node is greater than its left child, but less than its right. The benefit of a binary search tree is that it's easy to locate a node when they are in order. So yeah, those are binary search trees. If you would like a copy of this code, I'll post this to the comment section down below. Don't be afraid to smash that like button, leave a random comment down below, and subscribe if you'd like to become a fellow bro.